but this problem is a magician with a human cannonball act, where they launch themselves over a couple of Ferris wheels and try to land in a net. And the velocity knot and the theta and the height of the net is given. I guess I'll call that H final. And also the distance to the first Ferris wheel is known. But the first part of the problem asks for the clearance between, maybe I'll call this H1, the clearance between the person as they're passing over the Ferris wheel. And it's not so bad, right? To do this, you just split this up into horizontal and vertical components. You realize that as they're flying up, they have some initial velocity that breaks into a, what do you call it? So V naught is going to break into a horizontal and a vertical component. V naught H, V naught horizontal, and V naught vertical, I guess. And the idea is that the horizontal velocity is just going to be V naught cosine theta. And the horizontal position is just going to be that horizontal speed multiplied by t. So far, so good. So using this position, you can basically figure out at what time he reaches the first Ferris wheel, and then plug that time right into the second equation, which is, call it delta y. So x is equal to this, and y is equal to that. So the first equation basically tells you, okay, the x is changing delta 1. We know v naught cosine theta, so then you can solve for t, and you can plug this t into the second equation in order to solve for whatever their height is, and that will let you tell you their clearance over the Ferris wheel. Simple enough, right?
Right.
Okay. Sorry, that was a bit of a monologue on my part. But okay, then they say if they reach maximum height over the middle wheel, by how much did they clear it? Ah, that's very interesting. So, do you remember what when they say part B, if he reaches max height, what is this screaming? What does this tell you about one of his properties? That's a very strange way to word it. But do you know what I mean? If you're at max height, what can you tell me about a component of his velocity?
0.
Yeah, right. Or specifically, velocity in the vertical direction is 0 at that particular point. So that basically, we're going to reuse this thing right here, but y is equal to v naught sine theta t max minus 1/2 gt squared. We are I think we're basically trying to find, again, what y is. And to do that, first we need to find t max. And in order to find t max, well, that's basically like saying, okay, if their initial speed was, so v final is equal to v naught sine theta t, v naught sine theta minus g times t max, right? This is basically saying this is their initial vertical launch speed, and that speed gets eaten away by gravity, second by second by second. And it's saying this is how many seconds it's going to take for all of that to get eaten away, and let Vf be equal to 0. So this equation basically lets you solve for t max, yeah? And then once you have that, you can plug that into this equation over here, and you get yourself your y. Pretty gravy, right?
Right, it all works out together.
Yeah. Like, I'm curious. I'm really curious to compare class to class. But one of the issues I have with some of the students from UCI who are in their mechanics class is that they really, really struggle. If I tell them this is a system of 2 equations and 2 unknowns, I would have expected that to be good enough for them to solve from right there. But most of them are not comfortable yet at that point. How do you feel about the comfort level, your comfort level in this class, and maybe what the professor expects here? Do you think that once you get to the point of seeing 2 equations and 2 unknowns, you basically just got it? Or
Yeah. It's just the fact of setting up what the unknowns actually are, because we don't actually see any real examples during lecture. It's just like a bunch of theoreticals.
damn. Okay. I know that's sometimes ways they teach physics where, they just spit out theory during class and expect you to figure out all the problem solving on your own. And I think that sucks. I think that kind of really sucks. But for problems like these, um, you might imagine that a student that's kind of immature is going to have to fumble around with a couple of kinematics equations before they find the one that I did that should hopefully make this all very clear. And I'm honestly not sure if there is a super cut and dry way to immediately know that these two equations are the one that you need to find. But for me, I guess working in retrospect, like I sort of basically just knew them right off the bat because I guess I'm kind of experienced. But like working backwards, we know something about the initial velocity in the vertical direction, and we know something about the initial velocity in the excuse me. We know how long that means that we know how long it's gonna take to get to zero because acceleration or gravity is acting on it, right? And then once you have that, we already had the equation from the previous problem that I just imported over. And this would tell me how high it is. And you notice for part B, unlike part A, we basically aren't worrying about the horizontal component at all. Because they gave us this condition that they reach max height over the middle wheel, it's almost like giving us the fact that I guess I should make this a little bit more consistent, but like velocity vertical final is going to be equal to 0 at the point of interest. Sorry, the point I was making is because they gave us this max height condition, it almost lets us not even have to think about anything horizontal in the problem, if that makes sense. Because it gives us, you notice that both of these equations are talking entirely about vertical movements, right? The fact that max height was told to us means that we get the second equation for free. Sorry if that was a bit of a ramble, but I hope that makes sense.
No, it does. It's basically the only reason we're using the horizontal equation is to find t.
Yeah,
or
that was the
time.
first problem, right? The first problem was basically because we knew the position of the first one, right? And the horizontal is kind of nice and predictable. Its horizontal velocity is just going to be consistent because there's nothing, no forces in the horizontal direction. So it basically almost acts as like a, what do you call it? It almost acts like a stopwatch for us. It just tells us what the time is. But once we get to the second one and we're interested in knowing the clearance above it, we don't need to talk about the horizontal one at all, because the fact that we have the condition that it's max height, so the vertical velocity is 0, means that, hey, we don't need you anymore. We got a condition of our own, and that's a vertical condition.
But we still need that time, right? From A, or
From
we don't?
No, I don't think we even do, because T max is basically, we can grab T max just by this equation where we know that the vertical velocity is going to be 0 at that tallest point. So we know what the initial vertical velocity is, and we know that the change in velocity is g times T max. Right? So this lets us solve for T max without any having to worry at all about the horizontal components. You see what I mean?
Yeah.
Okay. And then C is how far from the cannon should the net center have been positioned, neglecting air drag. How far from the cannon? Okay. Gotcha. So the thing about the net is that it appears to have some height to it, right?
4.5.
4.5. That's right. So what that 4.5 is screaming is basically you to use this equation again and just let the change in y be equal to 4.5 or 5 or whatever the height of the net is. So let this be height of net. And that's equal to v naught sine theta t. I guess I'll call it t net to reach the net, minus 1/2 g t net squared. Now, one of the things that we should sine theta. One of the things we ought to know about. So, the big direction here is that whereas the first problem we knew how far something was away in the horizontal direction, that let us find t to plug it into the other equation and find the height. Part C is sort of asking us to do it in a different way, right? Instead of knowing a horizontal displacement, now we know the vertical displacement from the start, which means that we use equation number 2 to find the time, and then plug that back in equation number 1 to find the horizontal displacement. You see how that's kind of like reversed almost,
Oh, yeah.
right? That's the really nice symmetry behind this problem, is that whereas the horizontal equation sort of acted as our stopwatch when it gets past the first Ferris wheel in the original problem. Now that we're aiming to shoot for the net, now it's the vertical equation that lets us know. My pen kind of dying on me here. It's the vertical equation that lets us sort of know when T net has been, what the time is that it's reached the height in question.
So they basically switch in purpose. So then vertical becomes the stopwatch.
Exactly. But there is just one little wrinkle to this. Is that the delta y is a quadratic equation, right? So we can solve for it just fine, because at this point we know the height of the net, we know the v naught, we know the angle and all that, and g. But it's a quadratic equation, so there's going to be probably two answers to t net. And you're going to have to choose the one that seems more reasonable. And physically, it's going to probably be... Unfortunately, you're probably going to get two positive answers, so it's not super obvious which one's the right one. But in a situation like this, we need to think back to the physics, right? If this is the height of the net, it's a couple meters off the ground, and they were initially being launched off the floor, you see how there's 2 points at which the trajectory crosses this horizontal line?
We want the one further to the right.
Exactly. We want the larger t value, right? From the equation's perspective, it doesn't know about the physical situation. All the quadratic equation is doing is saying, hey, you gave me this vertical expression. You gave me this equation of motion in the vertical direction. I don't know anything about horizontal right now. All I'm going to tell you is the time it touches the height. Sorry, the 2 times it touches the height that you gave me, right? And you have to basically use your judgment in a situation like that. And we know that the guy's going from like left to right, and the net is as he's coming down. So we want the larger time. Exactly. Yeah. And once you have that, well, you know the horizontal velocity, right? So you just give that time into this equation, and boom, you know exactly how far the net needs to be positioned. Makes sense, right?
Yeah, it actually a lot simpler than I thought it was going to
Okay.
be.
All right. I'll end the recording.